Welcome back. So next subject is a talk by Mr. Greg Snider, who is a senior architect of Information and Quantum Systems Lab in HP. And his talk is Memristors as Synapses in a neural computing architecture. So let me briefly introduce Greg's background. He received his Master's of Science in Electrical Engineering from Stanford University, and he has worked in the many different fields, medical instrumentation, telephony, image processing, network protocols, operating systems, and programmable logic, among others. And Stan mentioned that was Greg who found the paper and made the link to all the experiment and the phenomena in their laboratory. So it's my pleasure to introduce Greg. Yes, thank you.
Okay, so I'm going to be talking about an interesting application for these kind of devices, which is a little out of the ordinary, and that's in the neural domain. And here's an outline. First of all, I'm going to spend about the first third talking about why neural, what's the motivation for looking at this, and also defining, what's meant by neural, because depending on where you went to school and when you went to school, you'll have a different image of what a neural net is, okay? It's widely used for many different systems. Second, I'll show you a mapping of the simplest neural circuit that's capable of learning and show how to map it onto a nano-memristive crossbar coupled with CMOS. And finally, I'll show a couple examples of learning or self-organization of this kind of a system. So first of all, if you went to school on the West Coast in the 80s, you're probably thinking something like this. You know, neural nets, they tried those in the 80s and they didn't work. And that's because, from the San Diego group, there was this sort of a revolution of feed-forward neural nets where you model a network with little circles being the neurons and the edges of this graph being the, quote, synapses. And you simply put signals at the input to this network and let them flow through this fixed function network, and out the other end pops a recognition of the input. So the input might be some, poorly drawn representation of, say, a number, but yet you get a nice crisp classification coming out the other side. Right? But this is a fixed function sort of a network. Okay, and this works really, really well. I mean, these kinds of networks are used all over the place for, and the post office uses them for reading zip codes off your letters. Banks use them for reading amounts off of checks. They work very, very well. Very mature technology. But they require high precision components, especially during the training phase when you're trying to compute exactly what the weights of all those edges are. You need at least 16 bits of precision in order to do the training. And the training method is basically just stochastic gradient descent. So mathematically, it's very simple. But another drawback, though, is that the learning, the way you train these things, is slow. It takes a lot of time to do gradient descent. And it's also unstable. So you can train these things to recognize certain sets of objects, but if you want to add new things for them to recognize, you can't do that without destroying the old memories. So they're unstable in the sense that you can't introduce new memories without doing damage to the old. That phenomenon is called catastrophic interference. These are also non-adaptive. You basically train them and you ship them out as a product, and they require external control, particularly during the training phase. But what you'd really like, if you're going to have some sort of machine intelligence, is, and also something that's economically viable, is the ability to use low precision components. So it can be cheap. You like fast, stable learning. People can learn things very quickly without forgetting old memories. You want something that can adapt to the environment and be autonomous. So how do you get these desirable properties? You're not going to get them with this kind of network up here in the upper left. So, I mean, this is a question that's been pursued for decades. And right now, there's really only one option on the table that seems viable, and that's to look at nature and biology, since biology has accomplished this. So the first step is to give up this idea that you have this fixed function, transfer function sort of network going through, and make your components dynamical. So these synaptic edge weights are not fixed. They evolve in time as a history of the signals that traverse them. And the same thing for the circular neurons. They also evolve in time, although on a different time scale. And so, instead of fixed function, you're talking about sets of differential equations in addition to transfer functions to characterize the system. You also have to add lots of feedback. Again, this is what nature does in brains. You've got feedback. It's not feed forward anymore. There's lateral feedback. There's feedback going backwards towards the inputs. And it's both positive and negative. And finally, you need to make it autonomous. You need to close the loop with the outside world. So this network has to be able to somehow interact with the outside world at its outputs, and through its inputs, observe the consequences of those actions in order to adapt and learn. So what you're really talking about, if we're using the brain as a model, is something that's very different from the 80s style feed-forward neural net. You're really talking about a stiff nonlinear dynamical system. So, okay, that's fine. So, why not just program this on a computer? Why don't we have these today? And the reason is that if we're pursuing this paradigm of a dynamical system for machine intelligence, it's really difficult to do. Stiff nonlinear dynamical systems are inefficient on digital computers. Here's one example, famous example. IBM's been doing lots of brain research, and they've been simulating part of a mouse cortex on their blue gene computer. And this particular simulation, you can see, you think it's a lot of neurons and synapses, but it's really only about a cubic millimeter of cortex. And even though the processors are running around a gigahertz, it still uses about 40 kilowatts of power to do the simulation. You compare that to the human brain, which runs only about 10 hertz and uses only about 20 watts to handle a system, more than 3 orders of magnitude more complex. So, I mean, you can do a dubious extrapolation here about, what it would take to do a human brain on a digital computer, and you come up with like a gigawatt and thousands of these blue gene racks. And of course, you could optimize this, and people have estimated, what if you really optimize the digital hardware for doing these kinds of simulations, and you can squeeze off another 3 orders of magnitude in the cost. But that still leaves a gap of about 5 orders of magnitude between what you can do in analog and digital for these kinds of systems. So that's really the opportunity. It's like here's a class of computation that we can't really do efficiently on a digital computer. And so the first thing you might think of is, well, brains are mostly synapses. That's the leading theory of where memories are formed, is in these synapses. Can we implement synapses using memristive devices? And there's several properties you have to satisfy. First of all, it has to be economical. You have to be able to, you don't want to build a brain that fills the size of this hall. It has to be small enough. And synapses in the human cortex, you need about 10 to the 10th of those per square centimeter. So if you want to achieve biological scale, you have to be able to achieve that kind of density. And this is incredibly dense in terms of today's technology. We're just on the edge of being able to put that many transistors on a chip. But we're talking about something with much more complex dynamics. And as I show here, we've been able to achieve this density and more with these memristive crossbars. And of course, they have to be dynamical. Synapses are dynamical in the brain. But a problem is that they have to have the right kind of dynamics. So on the left, I've shown a very simple dynamic for a synapse. Brain synapses don't look like this. This is one of the simplest possible models. But even though this simple model actually is capable of learning, it's very different in form from the kind of dynamics we see in the memristive nanodevices we've been making. So what do? You know, it's like you got the first two right, but the third one doesn't work. Well, you can talk about changing the dynamics of the memristive devices, but that can be hard to do. But you have another degree of freedom, and that is instead of trying to change the dynamics of your devices, live with them and change the neurons instead. So what I've been working on are transformations that allow you to take synaptic networks of, you know, biological-like synapses and neurons and transform them to equivalent functionality memristive networks that combine CMOS quote neurons and memristive quote synapses. I put quotes around both of these because the neurons in this transformed system don't behave the same way their biological counterparts do, and neither do the synapses. But that's okay, as long as the net behavior of the system is the same, that's what you want. So now I'll give you a quick introduction to how you can use these things to do learning. So we have these synaptic devices formed, as Stan mentioned, you know, at junctions of crossing nanowires separated by some memristive material. And I'm going to oversimplify here quite a bit. And I'll call I'll pretend that these devices are linear in their transfer functions, and I'll call the conductance of them W. And here's a rough, this equation up on the right is an approximation of how they behave. This differential equation, there's a decay term, which can, depending on how you design the devices, can be months, years, or who knows, you know, centuries. But what's interesting here is actually the right-hand side, that there's this incredibly nonlinear switching term. And I'm going to focus just on that cinch function, because this is actually what makes these devices so interesting. Is, you know, if you look at, for a given specific value of conductance W, if you look at the function, the derivative, how that conductance changes as a function of voltage, it's very nonlinear. And for example, at a low voltage, you can get very negligible rates of change in the conductance. But merely doubling that voltage can give you orders of magnitude increase in the rate of change. Okay? And it's this extreme nonlinearity in the differential equation that's really crucial and allows us to do this transformation from biological synapses to electronic synapses. And so I'll just sketch out how you can take advantage of this to do a biological synaptic learning law. So here's the trick. This is the simplest possible case. We do something really goofy. So neurons in biology communicate by sending spikes. You know, they're all about a millisecond wide and all about 70 millivolts peak. And they send them to each other. Electronically, though, we have to do something a little bit different. So now, in this approach, I'm showing two neurons with these strange little triangular-like symbols, trying to communicate with each other. The one on the left is trying to send a signal to the one on the right. Now, here's the change from biology: is they don't simply send a single pulse. They send a pair of pulses, a positive going and negative going. And this is true for both of them. The presynaptic neuron will send a pulse pair forward. The postsynaptic neuron will send a pulse backwards. This is a synchronous system. And because of that nonlinearity, shown here in the bottom left, if the negative going pulse from the forward going spike pair overlaps with the positive pulse on the backward spike pair, you get essentially constructive interference. You get a voltage drop across the memristive device in the center that all of a sudden is twice as large as either one of the single pulses alone would induce. And because of this nonlinearity in the derivative, whenever you get this overlap between these two pulses, one forward and one backwards, you can get a very rapid change, an increase in the conductance of the device. And I won't go through the details of this, but by a few enhancements of this, you can actually take this one learning law here shown in the middle. This is called an instar learning law. Actually, it's on the bottom here. this is called an instar learning law, and do a stochastic approximation of this learning law. But there's other problems to be solved here. It's not just getting the synaptic dynamics right or the neuron dynamics right. You also have to worry about wiring these things up. You know, you're talking about 10 to the 10th synaptic devices or memristive devices on a square centimeter, you know, talking to about 1 million neurons all in CMOS. How do you wire all these things up? And you know, if you look at like a very simple, this is on the left is one of the simplest neural networks, recurrent neural networks that does something useful. And it does learning in stationary environments. It can learn patterns. And I'll explain a little bit. The squares here represent neurons. The edges are connections between neurons. Signals come into the bottom. Each one of these square neurons on the bottom fans out the input signal. Those little yellow dots are memristive devices, which are electronic analog of synapses, going up to a top layer of neurons. And then this top layer of neurons actually sends signals among themselves. This is negative feedback across these top neurons. So you've got excitatory inputs coming up from the bottom layer through these memristive devices as synapses, which will change over time, going up to the top layer, which fight each other with negative feedback. This is known as a competitive network. But just from an electronics point of view, you figure out how you're going to lay this out on a chip. You know, there's crossing wires. You know, the edges of this graph have to be memristive devices so they can compute. And how do you lay this out? Well, it's actually pretty simple. You just do a little shifting around. The topology is easy to achieve. You take this simple bipartite graph, and by simply moving the neurons around, you can turn it into a crossbar structure. And then by taking the neurons, the square along the edges, and distributing them uniformly within the area and rotating the crossbar wires, you can achieve a nice regular layout for your neurons and synapses and forming these crossbars. And so here's basically sort of the idea what this would look like. The idea here is on the lower right here, each one of these little gray cubes would represent a neuron implemented in CMOS. This shows 4 neurons. The blue represent nanowires sitting on top of the CMOS, connecting down to the CMOS through these little black metallic pads. And then the yellow that you see here are the memristive nanodevices themselves, and they're serving as the synapses. And it's that slight rotation of the nanowires that makes this thing work. It basically allows every neuron to be able to talk through memristive devices to a neighborhood of other devices in a very simple and regular way, and enable us to implement this basic kind of neural circuit. And from a fabrication point of view, it's conceptually simple. You start off with a CMOS substrate that implements the neurons, and you simply lay down a layer of nanowires that serve as the axons or the outputs from your neurons. So these would connect to half of the pads on the CMOS neuron. It would be connecting down to the outputs of your neurons, conceptually on a memristive layer, and an orthogonal layer of nanowires which serve as your dendrites, which are the inputs to your neurons. So a very simple scheme allows you to implement this competitive network shown here on the right in this conceptually simple structure that can be fairly easily fabricated. So I'll finish up here with a couple of examples. We've actually done simulations of these kinds of networks, memristive networks. And so here's a very simple problem that you might come across, and that's independent component analysis. How can you learn the independent components of something, some sort of sets of input signals, which could be some kind of sensor array or something like that. So for example, say you have a vision system and you want to do something like I was showing earlier where you're trying to recognize handwritten digits. The first step in the processing to recognition might be to break down the handwritten digits that you're seeing as input into some independent components. So the question is, what is a basis set for representing handwritten digits? Well, this kind of a circuit actually can be done. Actually, these neural circuits are good at this kind of processing. You can feed in this training set into this Memristive network and let the thing train. And over time, it actually extracts the independent components, which in this case, for this example, if you're feeding in these handwritten digits, the independent components are little tiny strokes. You can kind of see here, there's kind of like some black ink. I wish I had a pointer. Surrounded by white. Most of these things are little tiny strokes of black ink surrounded by the white paper in the background. Okay? So you can express these digits as a small number of these little tiny strokes summed together, right? So you've essentially extracted the independent components, your basis set for representing these handwritten digits. So that'd be like a first stage in processing. Of course, you have to do much more than that. Oh. Thank you. So now I don't need it. And then the final example is, this is fine for handwritten digits, but what's the basis set for representing natural images? I mean, if you're building a vision system, you're going to want to be able to deal with the real world. And it turns out the independent components of natural images are edges. Edges between edges and within images themselves. And so here's a simulation of a Memristive network learning to find those independent components. This is under simulation. This is about 3,000 neurons, 130,000 Memristive synapses using the simple equation I showed earlier. And it actually does self-organize to form these receptive fields. What you're seeing here in these each of these little squares is one of the components that the network has learned to extract from the inputs. And you can see they correspond to edges of various orientations. So for example, here's one that corresponds to a vertical edge that's black on the left side and white on the right side. And these things are actually nicely uniformly distributed over the space. But the thing that's critical here is that there's no programming involved here. This is all self-organized, right? We didn't go in there and configure each one of these 130,000 Memristive devices to be in some state. They just naturally evolved to that state as a function of the dynamics of the network as a whole. So another thing that Stan mentioned is the problem of device crumminess. We want to make these things really small, but in practice what happens is you get lots of device variation. They don't all behave the same way, and lots of them just don't work. So biology, of course, deals with that very well. You lose tens of thousands of neurons every day, and yet you continue to move on. Is this true for these kinds of Memristive networks? This is a study, a simulation of that very first question. What I did is the orientation map I just showed you on the last slide, I did that same simulation over and over again, but randomly injecting defects throughout the Memristive devices. I either would make some of them just totally open, stuck open, so there's no device there at all, and other times I'd make them stuck closed, so they'd be short-circuiting the 2 nanowires that form them. And experimented what happens to the quality of the edge detectors as a function of defect rate. I think this thing's dying. Up to about 20%. The vertical axis on this chart here is a metric for quantifying the quality of these spatial filters. And you can see as a function of defect rate, either to stuck open or stuck closed defects up to about 20%, there's a very graceful degradation in the performance of the network. Okay, this is stunning. I mean, we're not used to this in digital logic. You know, a single transistor in a CPU can kill it if it goes bad. But here has very little impact. So this economically is interesting because it offers the possibility of making these things really cheaply. Always a good thing. So to summarize, the vision that we're pursuing here and exploring, and actually under a DARPA grant, which we're grateful for, is this vision of analog computers that complement digital, all based on these Memristive nanodevices. You know, the ability to build autonomous systems that adapt on their own in real time to a complex and changing world. This is a capability that's beyond what we can do digitally. So I'll take some questions.
So we are recording, so when you ask a question, could you repeat the question
Sure.
and then answer?
Ooh, I'm hard of hearing, so I may not be able to even hear it. Is there a microphone?
Yes.
Greg, biological systems have degeneracy, which allow them to adapt and essentially have a form of redundancy. How would you decompose that into a redundant system to allow for that degeneracy?
Well, that's
Can
essential.
you repeat the question?
The question was about redundancy in the system architecture. Yeah, the kinds of neural models we're studying have enormous amounts of redundancy. That's absolutely essential. Without that, you can't make these things reliable. And you also wouldn't get the kind of defect tolerance that you see here.
Yeah, because biological systems actually, I think it's degeneracy is not redundancy, but they form multi-functions. In a sense, you don't have that. So you would have to have redundancy to accomplish the degeneracy that biological systems have.
Yeah, I mean, here I'm only able to show a very simple case. We're looking at much more detailed models, but it wasn't possible to present those here.
Any other question? Otherwise, we will move on. Thank you very much. Greg. Please, with a souvenir.
Thank you very much.
Thank you very much, Greg. Very exciting. You know, Greg's presentation reminds me when I was a graduate student trying to work on modeling under the guidance of Leon. Thesis was on the modeling, and you know, modeling is about synthesis of dynamical systems. So I hurriedly went to library in Evans Hall. Next building is a mathematics building, and tried to find the book. And after many days of search, finally I found one book called Synthesis of Dynamical System, and it was authored by a British mathematician. I was so pleased to find it. I opened the first page. What it says was, this book is dedicated to my wife, a dynamical system that cannot be synthesized. I am pleased to introduce next speaker, Dr. Rainer Wasser from Germany. Actually, you know, after we identified this excellent speaker, we tried very hard to bring him to this symposium. He said, I cannot come because I'm fully committed to many different things. But kindly, finally, he rearranged his schedule to come to this meeting. So I'm very grateful. And let me briefly introduce Professor Wasser, who is a professor of physics at the Faculty of Electrical Engineering and Information Technology of Aachen University. He is also director at the Institute of Solid State Research at the HGF Research Center in Juelich, Germany. He received a PhD in physical chemistry at the University of Darmstadt. And his group is focused on fundamental aspect of electronic materials, integrated devices as non-volatile memories. He has international collaboration with the scholars in US, Europe, and Far East. And he was honored with the IEEE Ferroelectronics Recognition Award in 2000. And since 2001, he has been the coordinator of research programs throughout Germany on information technology and nano-electronics. Dr. Wasser, thank you.
Thanks a lot. Yeah, perhaps we put that down. Perhaps, Professor Kang, just a little correction. I was coordinating it within the Helmholtz Association in Germany, so that's a bit smaller than Germany in total. It's still large, but it's larger than Max Planck, but anyway. Okay, that's fine. But it's okay. It could work. Okay, so now it's working, it's fine. The wireless would not be bad, I must say, but I can also stand there. Fine. Switch it on. Yeah. So first of all, of course, I would like to thank the organizers. Sorry about that. Stan Williams and Steve Kang for inviting me here on the occasion of celebrating the famous invention of Leon Chua and the realization by the group of Stanley Williams. And I would like to talk about the Redox-based systems, Memristive RRAM systems. RRAM stands for Resistive Switching Random Access Memories. And I would like very briefly to introduce the basic ideas, which I can really keep brief because it has been done throughout the morning. And then I will focus on two systems: cation migration redox-based systems and the anion migration, meaning oxygen vacancy-based redox systems. So before I start, I would like to acknowledge the work which has been done by the people of my group, which is Christoph Schott, Herbert Schröder, Regine Dittmann, Shibuya, who is an Humboldt Fellow, and then our PhD students, Ruth Münstermann, who is now in a research stay at HP Labs, Tobias Menke, Sheng Wang, Christine Schindler, who left already to Siemens, and Carsten Kügler, who is the head of our nano-architecture lab. And there's an acknowledgement to many people, certainly beyond this group, and many funding agencies. Now, concerning the Memristive devices, we have heard many effects already in the morning, and I don't want to go through all of them now, but I would like to mention that I would like to focus on the electrochemical metallization cells, or the cation migration-based system, and the valency change effect, which means valency change in transition metal oxides based on the ion migration. So I summarize them as redox-based switching phenomena in chalcogenides. Oh, now it starts again. Sorry about this. Okay, the systems which we are considering are, as you know, metal insulator metal systems, or perhaps one should better say metal resistive metal systems, where the two metals or the two electron conducting connections are often not the same, either in a capacitor-like structure or especially for research lateral structures. Often we need forming, not always, but sometimes, or in many cases, we need forming. That means you have to apply a certain electrical stress in order to form, for example, switching filaments, which you later can switch. And the forming process usually takes somewhat longer time than the actual switching. The write, which means set or reset, is done by pulses of few volts, and desired write times, as we have heard already, is below 100 nanoseconds in order to compete with flash, or to be better than flash. Preferentially, preferably it should be lower than 10 nanoseconds. And the read operation is done at a much lower voltage, few hundred millivolts, for example. And here you have to take into account that you want to have a retention of 10 years at 85 degrees centigrade. So bipolar switching, and that's the topic I would like to talk about. Bipolar switching means that you have one voltage polarity where you get a set operation, where you switch the system on into an on state, and at the other polarity, you get the you switch it back to the offset. You reset the system. So that's a bipolar operation. Discussed in the field, of course, is the, let's say, localization of the switching event. The dependence on the electrode area. Often you find it's very localized, filamentary. That's what we are mainly studying, although we sometimes find the other system as well. And you can, under some circumstances, have a somewhat distributed system as well, as has been shown and stressed by Sava. Now, first system are these electrochemical metallization memories. So names are different. You find them as PMC, programmable metallization cells, or conductive bridge RAM, and whatever. Operation is as follows. The switching, the on switching is you use an electrochemically active electrode material, which is silver or copper or a few other metals. You have, that's 1 M if you have the MIM system. So 1 would be here the silver, for example. Then you have an ion conductor, and then you have an inert electrode, for example, platinum, iridium, and so on. And the filament, the on switching, is conducted in a way that you have a dissolution of the active element, silver. You form silver ions, which move through the solid electrolyte or the electrolyte, and then is deposited on the other side as silver, and silver filament grow back and then make a short circuit. That goes back quite a while to Michael Faraday and is quite well understood. The off-switching is just the opposite effect, electrochemical dissolution of this filament. Electrolytes are also widespread, amorphous germanium selenide or sulfides, but can also be disordered amorphous sulfides, oxides, and many other things. History, briefly, is that Hirose and Hirose have shown these nice filaments between electrodes in the lateral cells. Kotziki has shown that you can work that into a memory. Aone has his famous atomic switch where he was able to confine that to 1 atom size. So to really see the Landauer conduction steps, the quantized conduction steps. And Qimonda succeeded in making demonstrator out of this, which were up to 2 megabit in size. So that's the brief history. We have been studying mainly silicon dioxide as a quite unconventional electrochemical metallization electrolyte. And here the system or the switching curve is shown once again. I don't want to go through all the details. You build up the filament, you make the connection, you get into a current compliance at this stage. You go back, and at the opposite polarity, you remove the system, you remove the filament, and come back to the original state. What we wanted to do is to look into the process, into the details of the microscopic process, and to see, especially to look for the rate limiting step. The kinetics is composed out of many subsequent steps, and you need to know the rate limiting step in order to see where you can control the system. So the overall process is as follows. You have the anodic dissolution. So you want to dissolve the silver into the silicon dioxide in this case. That is an electrochemical electron transfer reaction. You don't need, in this case, at this site, you don't need an overpotential. You don't expect an overpotential, but this electrochemical transfer reaction is highly nonlinear. It's an exponential dependence on the voltage. Then you have the cation transport. You need to transport the cations through the electrolyte. That is by drift diffusion, and because of the high fields, it's mainly by drift. That's just by drift. And that is mainly linear. At the cathodic side, you have the deposition of, you have an electron transfer again, but now a reduction of the silver ions to silver, and you need to nucleate and crystallize the silver particles in order to build up the filament. Here we have a highly nonlinear electron transfer reaction as well, and we expect a crystallization over potential. I would say, of course, if you were electrochemists, because they would know that from the training. Filament growth. The final part is that the metal filament, of course, needs to go through, and you can say that the winning one, the winning filament, the fastest one, because of field confinement, gives the shot, and it's just one spot. Now, what did we do? We used systems with thickness of silicon dioxide in the range between 5 nanometer and 20 nanometer. Silver on one side, platinum or radium on the other side. Now the forming, also here you need forming, and we found that the forming needs much higher voltages than the actual switching. And if you look at the thickness dependence, you find that the forming linearly depends on the thickness of the film. So obviously here for the forming, the drift seems to be, the transfer seems to be rate limiting. But after that, after you have formed this channel first time, and you switch it off and on again, then you stay at this cycle here at a much lower switching on voltage, and especially you don't have a thickness dependence anymore. The voltage, the switch on voltage, is not depending on the thickness of the electrolyte anymore, and that means the drift, also for some other reasons, but that's the main one, is not rate limiting the switching. If you look at the kinetics of the switching, so if you plot the speed which you apply, for example, the ramp rate, here we have taken the inverse of the ramp rate, and look at the dependence of the switching on voltage, or the set voltage, then you see that's an exponential dependence. So if you go down to pulse measurements, so this was done by triangular sweep measurements, and in addition we have got pulse measurements. So it's going over many orders of magnitude in the sweeping, in the actually kinetics which you set, and you look at this at the voltage, and you see that's an exponential dependence, and not even that, you have also a threshold voltage, and that means that obviously for the application you can guarantee a fast switching and still a long retention time. That's of course essential, as Greg just explained to you in detail. And from the understanding point of view, that means that obviously the cathodic, the process at the cathode is rate limiting. That means if you want to modify the kinetics, if you want to turn the knobs, that's the point where you have to act. Yeah, the cationic electron transfer is rate limiting. And how does it proceed? Now, there are two possibilities. First, as I mentioned, the Butler-Volmer equation, so the electron transfer. So you see it's a exponential dependence. This eta here is the overpotential, so the deviation from the half cell potential, and you have got alpha as a certain asymmetry factor. But essentially, you have got this strongly nonlinear dependence. But there's another possibility: the nucleation over potential, the potential which you need to form the first nucleus. It's also depending exponentially on the overpotential. And at the moment, we cannot distinguish this. We know we have studies going on concerning the size dependence, but at the moment we can only say the reaction certainly is limiting. The rate limiting step is at the cathode, and we see this. We can explain the exponential dependence on the voltage, but there are two possibilities. One additional way how to proceed is to model the overall process, for example, by molecular dynamics, looking at individual ions which are dissolved at the anode and which look for which are under the influence of the field and the concentration gradients, and you have the electrode reactions in addition. And here I wanted to mention the growth speed of the nanofilaments. If you calculate roughly the growth speed which you get at a nanofilament of, for example, for a current of 1 microamp, then you find that the speed, the formation speed, if you have one filament of 10 nanometer diameter, which is probably too much still, is 1 meter per second. Sounds little, but if you have a gap of 10 nanometer, that means 10 nanoseconds. And probably that's overestimated anyway because the filament will be smaller. The reset operation has a certain issue because during the reset you have a symmetrical system, silver on the one side and silver on the other side. And you need to know where it's dissolving, where the dissolution starts. And as we have shown, obviously it is a geometrical effect. That's important, especially for the configuration of the later cells, which you want to build up into the nanoscale. Okay, let me come now to the second issue, the second kind of system, type of system, which is based on valency change within the transition metal oxides, and which is conducted through the migration of anions, the oxygen vacancies. As you have seen already, that has been found for many systems, zirconates or manganates or titanates, or titanium dioxide. The strontium titanate single crystals has been used as a model system quite often. The characteristics is that after a forming process, there's a reversible bipolar switching between stable impedance states, and it's bipolar switching. Okay, if we want to understand this process, then we should first look what is known about oxygen vacancies. So the working hypothesis was oxygen vacancies are the driving species, and you need to look into the point defects, the ionic defects, the valencies for strontium titanate, where I want to stress that the active point within the strontium titanate is the titanium dioxide, because that's undergoing the reduction and oxidation. So if you look at a typical point defect diagram for strontium titanate, then you see that you have got the relative defect concentration, and this can be tuned by the ambient oxygen partial pressure, which you can control over many orders of magnitude. Technically, you can only go up to here if it's in bar, of course. And at the high temperature, you get equilibrium. So you can find at the system, which is, let's say, slightly acceptor doped, and you have a compensation by oxygen vacancies, you find electron conduction at a high temperature and hole conduction under oxidizing atmospheres. And if you quench down, then you would quench in a way that, for example, on the oxidizing side, you would reduce the carrier concentration of the holes by some orders of magnitude. That's because the acceptor states are much deeper in the valency gap, in the band gap, than the energy states of oxygen vacancies, for example, or of other donors. So that's what you would expect to see. These are equilibrium states if it's HT, and if you quench down to LT, to low temperatures in the range of the operation temperatures of devices, then you would expect this. Sometimes it's argued that these diagrams, which have been recorded and calculated thermodynamically for single crystals, for ceramics, for bulky materials, do not apply to thin films, especially since thin films are usually deposited at much lower temperatures. So you would not establish the defect disorder, which you usually find, the Schottky disorder, at high temperatures. We tried PLD-grown thin films, epitaxial PLD-grown strontium titanate films, and indeed found that the high temperature behavior is qualitatively, at least, very much as we would expect. You find these characteristic slopes in the diagram versus the concentration or the conductivity versus the log oxygen partial pressure. That's exactly what you expect from the calculations, thermodynamic calculations. So it cannot be too far away. Of course, these are single crystals, and we have to consider that in especially nanoscale, the extended crystalline lattice is quite restricted. So there are boundaries, there are surfaces, and there are extended defects. One of the extended defects is grain boundaries. Grain boundaries, especially if you grow non-epitaxially on certain metals, you have them all around. So what would you expect if you look at such a model system, undoped strontium titanate? You can also take titanium dioxide, which have a certain amount of accepted type native defects, which are compensated by oxygen vacancies if you anneal under reasonably high oxygen partial pressure. So under these conditions, the grain boundaries will find themselves in a situation where grain boundary states are donor types. So you find a depletion of the p-type conductance and the oxygen vacancies near the grain boundary core, and you find an increase, or you find a core along the grain boundaries which is n-conducting because of the donor states. And that has been shown for quite a range of different strontium titanate ceramics. You can trace that down even to low-angle grain boundaries where you have pearl chains of dislocations. You can see here these pearl chains of these nice dislocations. And that brings me to the point where the switching, the forming and switching sets in again. The dislocations you find all over the place, even on single crystals. So if you do edge studies and you look at the edge pitch density, you find high edge pitch densities for strontium titanate single crystals, for example. Usually arranged along lines and bunches and bundles. And recently, Schott in our group has been able to see that within one edge pit, which in one groove which came about by the edge process, chemical edge process, after reduction anneal, that the center of this pit is identical to a highly conductive element, to a highly conductive spot. And that confirms our hypothesis that the filaments, the hot spots, which we usually observe by conductive tip AFM measurements, are in fact dislocations, and the exit of the dislocation within the single crystal, strontium titanate single crystal, pointing towards the surface, is the situation where the action actually happens. And if we now look at the electroformation, if we consider this framework of knowledge on the point defect chemistry, the extended defect chemistry, I've shown you only a small part of this, so there's many more types of extended defects. And if we now apply a voltage to a cell, for example here, platinum, strontium titanate, slightly iron doped, I tell you why in a moment, slightly iron doped strontium titanate single crystal platinum cell, then from the basic drift diffusion calculations you would assume for low voltages which you apply, you see 3 millivolts to a single crystal, you would assume you would find a linear dependence, a linear slope of, for example, the oxygen vacancies. Here it's a log scale, but you see how stretched it is You see why it's locked in a moment, but I tell you it's linear, and you can even analytically calculate that. That's textbook knowledge. It's quite simple. So that's what you would expect. What happens if you apply much higher voltages? So some time ago, in fact, almost decades ago, we did that for completely different background than today. Certainly not Memristors. At this time, you have published your famous paper, but I didn't read it. And I was active in a completely different field, meaning the long-term stability of titanate-based capacitors under DC stress, which is exactly what we are discussing now, but on the nanoscale. At this time, it was much larger, of course. So what happens now if you take such a model system and apply a higher voltage, for example, 1 volt, which is at least much higher than 3 millivolts? You find that the overall behavior is not linear anymore. It's, you find that if you have the anode here and the cathode here, the oxygen vacancies all move over there. They form a region near the cathode which is enriched by oxygen vacancies, and depletion near the anode by many orders of magnitude where the oxygen vacancies are just removed. And you can, that's taking us to the iron doping, the slight iron doping of 0.1 atom percent in the strontium titanate. If you put iron as an acceptor in that, then you can follow, you can trace this behavior, this concentration polarization, which I have shown you by the electrocoloration. So in the beginning, you have got a slightly reddish, completely homogeneous single crystal. You look at the single crystal slab, it's a thin slab, you have the electrodes on the side, and you apply voltage at somewhat elevated temperature, and you see that this dark red front emerges from the anode. And that's the region where the oxygen vacancies are so much depressed in concentration, and near the cathode, this reddish color is removed. And in fact, if you plot the calculation just along the same calculation which I used for the concentration profiles of the oxygen vacancies, if you look at the current density, the leakage current density through the system, you see that along with the process, you find an increase by some orders of magnitude. Now, that's homogeneous systems. At this time, we did not look into the details, into the microscopic details. That's done in the last few years in connection with the resistive switching. And if you look at the front of the electrocoloration, then Christoph Schott has found that it's not a homogeneous behavior. It is quite localized along, as we have many indications, dislocations. And there's a network of dislocations, and along this network of dislocations, the front is proceeding from the both sides, and we are looking for the cathode for good reason. If you look for the oxygen vacancies, which are accumulating near the cathode, then during the electroformation, and that's the sense of the entire system, no, I need perhaps the arrow. So that's the model idea. We apply a certain current to a macroscopic sample. We have indications that the oxygen vacancies accumulate near the cathode and form within these networks, they form a virtual cathode, which finally bumps into the anode, and then the voltage breaks down, so the resistivity breaks down at that point. So that's electroformation. Now, the actual switching can be done also by conductive tip AFM, and we have shown that you have little spots, hot spots, after a certain preconditioning, the exits of dislocations at the surface of strontium titanate single crystals, which you can let's say, switch back and forth by applying the right voltage to the tip of the conductive tip AFM. So that's these small spots, and these spots can be as small as 1 to 2 nanometers, as Stan has mentioned already. And the idea is to go not for single crystals, but for thin films, of course. So we repeated the whole experiment for epitaxial strontium titanate thin films, and in fact, we can write all, let's say, large areas and set them back. And in the beginning, and other people have seen that as well, people believed that what you see here is noise. But if you zoom in, you find that the noise is consisting of many individual spots, and they are not fluctuating. They are always at the same position. And finally, you can, by some correlation, find that really you deal with extended defects, mainly dislocations, but also other extended defects. So the idea behind that is that you form the filaments in a way that you remove the oxygens, or you introduce oxygen vacancies into the filaments, which partially reduces the neighborhood, the titanium sublattice, and the titanium 4+, which is insulating, would be turned into titanium 3+, which you can attribute to a semiconducting state, and then titanium 2+, which is metallically conducting, as Stan has already mentioned. And that's the way you would build up the electroformed state. And with the tip, you would then switch just the, let's say, the exit by removing the last part of the oxygen vacancies or putting them back. And by this electrochemical step, you switch from a, let's say, metallically conducting material into a semiconducting material, and you switch from the on to the off state. Of course, with a tip in vacuum or in some gas atmosphere, you would not build up the Memristive devices which you are interested in. So you need top electrodes, and we studied top electrodes, for example, platinum top electrode on thick epitaxial films, 750 nanometer. These films are thick enough that you see the depletion layer, so the Schottky depletion layer, because of the high work functions of the platinum top electrode. And with impedance spectroscopy, you can see what happens during forming. So in the unformed case, you find two semicircles which merge into each other. The second semicircle is just too large that you cannot see it on the scale. During the forming, obviously, you have the formation of this virtual cathode growing through along filaments and making contact then to the top electrode, and in the formed state, you just find one semicircle. And in switching, obviously, you switch back and forth this contact point by moving back and forth the oxygen vacancies and focusing then. Of course, this system has to be fast enough, and the electroforming is indeed not a real fast process, but the switching is. And we have shown that, in fact, for titanium dioxide and little cross points to be smaller than 10 nanoseconds. And along the numerical simulation of the concentration polarization, which I've shown you before, which I did for the degradation studies for the capacitors long time ago, we went and did a simulation where we introduced different boundary conditions for the two electrodes. First, we studied the electrodes in more detail, having the electrochemical Helmholtz layer on both sides. But in this particular case, we needed to have different boundary conditions concerning the, let's say, release rate of oxygen during the electroformation. But if you do this, then you find indeed a switching behavior during the simulation. And that brings me to the nice work of the HP group, because they did something more. What they did is they, as Stan presented, they introduced a graded system. So between two platinum electrodes, it's an oxidized titanium dioxide and a reduced one. And by this clever trick, you introduce the bipolarity, and if you tailor this further, then you get a real stable system where the asymmetry is laid within the electrolyte. And I took the liberty to show the numerical simulation for these systems with the graded electrolytes, because it has been accepted, Stan. This shows that, in fact, if you take all the different process steps into account and you use numerical simulation, you find the on-switching and the off-switching in all details and in all aspects with different parameters. So it's a beautiful work. I would like to come to my conclusions. Now, the prospects I mentioned in the beginning, prospects and challenges. The prospects have been addressed in the morning quite widely. So the ultimately high scaling potential for both the cationic and the anion migration resistive switching concepts, so with memristive concepts. The scaling potential really goes down to the size of the filament, and if you are able to have filaments, either metal filaments or the filaments which are based in the nature of the transition metal ions oxides, then you can get down to few nanometers, and that's actually the ultimate limit, because below this you run into the tunneling problems between neighboring cells. So that's huge potential which has to be addressed. Functions beyond pure memory has been addressed by Greg a moment ago. It's technologically compatible with CMOS to the CMOS interface. That's also important in order to get it emerging. Challenges are still quite high. We need highly scaled interconnect lines. That's a point we still need to address. Long-term reliability. Stan mentioned already a few aspects, but the, let's say, details still have to be followed up. The design rules are not known yet. Few things we see, but the real rules, the real, let's say, handle in a way that you have a guided search in the materials treasure map. The large variety of, for example, the transition metal oxides, but also for the electrolytes for the cation-based cells. That is not yet done. So it's still a lot of work for you, for example. Yeah. And the defect engineering. If our hypothesis is correct, then we need defect engineering, and that is just at the beginning. So ideas are, for example, that you have some vicinal surfaces. You will see misfit dislocations growing on a regular pattern, and you can use that in order to have a regular pattern of dislocations which you can use to switch, just for an example. Okay, with that, I would like to thank you for your attention.